We are now going into the last section of Chapter 1, 1.3, and the title is Initial Value Problems. An initial value problem, its acronym is IVP, is a problem that consists of a differential equation accompanied by a set of initial conditions. Let us firstly understand the meaning of a first-order initial value problem. For a first-order initial value problem, or we can simply call it as a first-order IVP, we are required to solve the differential equation which is of first order. So this is the general expression for a first order differential equation given by dy dx equals to f of xy. Once we have solved this first order differential equation, its solution must satisfy a prescribed condition which we call it as an initial condition given by y of x naught equals to y naught. So this whole set of problems where we are required to solve the differential equation which is of first order subject to the given initial condition is known as a first order initial value problem. Now let us look at the geometric interpretation of this first order IVP. Okay, now this is the first order differential equation. Its general solution contains a one parameter C, and that C can be of any value. In other words, the general solution generates infinitely many particular solutions. So suppose these are the graphs of the infinitely many particular solutions. So first graph, second graph, third graph, and so on. But out of all these solution curves, one of these curves has to satisfy the given initial condition where the curve has to pass through the point with coordinate x0, y0. Okay, so suppose this is the only curve that passes through the point x0, y0, and therefore we call this curve as the solution for the given first order initial value problem. Okay, example of a first order IVP is as follows. Solve the first order initial value problem given by dy dx equals to xy subject to the initial condition y of 0 equals to 3. What does this mean? After we have solved this first order differential equation, we must ensure that the solution satisfies this initial condition where the solution curve passes through the point with coordinate where x equals to 0 and y is 3. So the coordinate is 0, 3. So the solution curve for this differential equation has to pass through the point with coordinate 0, 3. Second order initial value problem. For a second order IVP, we are required to solve the differential equation which is of second order given by d2y dx squared equals to fxy y prime. Once you have solved this second order differential equation, we must ensure that its solution satisfies two initial conditions which are y of x naught equals to y naught, y prime of x naught equals to y1. So this whole set of problems where we are required to solve the second order differential equation subject to two initial conditions is known as a second order initial value problem. Let us look at the geometric interpretation of this second order IVP. Okay, suppose in this figure we sketch all the solution curves for the second order differential equation, but one of these solution curves has to satisfy these two given initial conditions such that the curve has to pass through the point with coordinate x0, y0. Okay, so this is the point with coordinate x0, y0. And not only that it passes through the point with that coordinate, it also has to satisfy the second condition where the slope at this point x0 is given by y1. Okay, so in this figure, m is the slope. So the slope at the point x0 is equals to y1. So out of all these infinitely many solutions, only one of this solution curve satisfies these two initial conditions. Therefore, this is known as the solution for the second order initial value problem. Take note that the number of initial conditions correspond to the order of the differential equation. That means if the differential equation is of first order, therefore for a first order IVP, there will only be one initial condition. For a second order IBP, there will be two initial conditions, and so we expect that for a third order IBP, there will be three initial conditions, y, y prime, and y double prime. And the initial conditions are all set at the common initial point x0. So let's look at the second order IBP. The first initial condition is prescribed at the point where x equals to x0, and the second initial condition is also prescribed at the same point x equals to x0. Example, this is an example of a problem involving a second order IVP. Solve the second order initial value problem. This is the second order DE, y double prime plus 4y prime plus 3y equal to 0, subject to two initial conditions, y0 equals to 1, y prime of 0 equals to 0. This means that after we have solved this second order differential equation, the solution must be a curve that passes through the point with coordinate 0, 1, and the slope at the point when x equal to 0 must be equal to 0. Let us discuss some examples. First example, find the solution to the first order initial value problem y prime equals to y squared, y of 0 equals negative 1. If the general solution to the differential equation is known to be y equals to negative 1 over x plus c. In this question, we are given a first order differential equation subject to an initial condition. So this whole set of problem is known as a first order initial value problem. And we are also given the general solution to this differential equation. And the general solution for this differential equation is given by y equals negative 1 over x plus c. We are asked to find the solution to the first order IVP given the general solution. So how do we go about solving this problem? Okay, so the solution is as follows. Now this is the general solution, y equals negative 1 over x plus c. Now we want to find the unknown c subject to this given initial condition. This initial condition states that x is equal to 0 and y equals negative 1. So substitute x equal to 0 in the general solution, substitute y equals negative 1, and let's see what is the value of c that we can obtain. Okay, so y is negative 1, x equal to 0, solve this equation, we get c as equals to 1. Therefore, this is the value of the parameter c based on this given initial condition, and therefore we say that the solution of the given first order IBP is as follows: y equals to negative 1 over x, and now we replace c by the number 1, y equals negative 1 over x plus 1. So this is the solution of the first order initial value problem. Take note that c equals to 1 is the only solution based on this initial condition. But if you change this initial condition, then you will get a different value for the c, and therefore there will be a different solution for the given IVP. Second example, find the solution to the second order initial value problem x squared y double prime minus xy prime plus y equal to 0, y of 1 equals to 1, y prime of 1 equal to 0 if the general solution to the differential equation is known to be y equal to c1x plus c2x ln x. So in this question, we are given a second order differential equation accompanied by two initial conditions, and therefore this whole set of problem is known as a second order initial value problem. And take note that for the initial conditions, they are set at the same common point x equals to 1. And we are also given the general solution to this second order DE, which is y equals to c1x plus c2x ln x. In this question, we are asked to find the solution to the second order IVP. So let us solve the problem. So we start by writing down the general solution, which we are going to refer it as equation number 1 for easy reference. Okay, y equal to c1x plus c2x ln x. Our aim is to find the unknowns c1 and c2 subject to these two initial conditions. So the first step is to use the first initial condition given y of 1 is equals to 1. It means that when x equals to 1, y equals to 1. So substitute x equals to 1 and y equals to 1 into equation number 1. So we get the following: 1 equals to c1 times 1 plus c2 times 1 ln 1. But ln 1 is definitely equal to 0, and therefore we can get the value of the unknown c1, which is 1. The next step is to substitute c1 equals to 1 into equation number 1. So we'll get y equals to, now c1 is already 1, so y equals to x plus c2x ln x, and we're going to recall this as equation number 2. Equation number 2 has an unknown c2 which we need to find, and we can get it by using the second initial condition, which is y prime of 1 equal to 0. But the second initial condition involves the first derivative of y respect to x. It means that we have to differentiate equation number 2, differentiate y with respect to x. Okay, so let us perform the first derivative of y respect to x. Differentiate x, you get 1 plus, now for this part here we are required to use product rule of differentiation. So let me call this as the u and the v. The u is c2x and the v is ln x. Product rule of differentiation, the formula is u v prime plus v u prime. Because the u is c2x, and then differentiate the second term with respect to x, differentiate ln x, you get 1 over x. So this is u v prime plus v is ln x, and then you differentiate the second term with respect to x, you get c2. Okay, so u v prime plus v u prime. The next step is to simplify whenever possible. Notice that we can cancel the x. So y prime is 1 plus c2 plus, and I rearrange. Whenever there's a product of a constant and a logarithmic function, it is best that we put this constant in the front of the logarithmic function. So we rearrange to get c2 ln x. Therefore, y prime is 1 plus c2 plus c2 ln x. We know that y prime of 1 is equal to 0, so substitute x by 1 and substitute y prime by 0. You get the following: y prime is 0 equals to 1 plus c2 plus c2 ln 1. Now ln 1 equal to 0, therefore c2 is negative 1. Okay, now substitute c2 equals to negative 1 into equation number 2. So okay, we already know the answer for C1, which is 1. So now we can get the solution of the given second order IVP, which is y equals to x. Now replace C2 by negative 1. So you get y equals to x minus x ln x. So this is the solution of the second order IVP subject to these two initial conditions. Again, if we change these two initial conditions, then definitely we will get different values for the parameters C1 and C2, and hence different solution for the given initial value problem. We have reached the end of section 1.3, which is also the ending of chapter 1. So in chapter 1, we have covered sections 1.1, 1.2 and 1.3. So please study all the materials taught in these three sections. Understand them very well. Learn how to solve the problems given in this chapter before you proceed to the next chapter, chapter 2. Thank you.